Okay, in this video we're going to start taking a look at some questions of calculating distances. And I want to start in 3 space with the distance from a point P, X, Y, Z to the origin, which is just 0, 0, 0. So we're going to be finding that distance. Okay. Now, to make things a little bit simpler, I'm going to work with a point that's in the first octant, at least for the picture that I draw. And once we've worked this out in the first octant, we'll take a look at our results and see whether they translate to other octants as well. So if we're working in the first octant, I would have a point, let's say here's my point P, but I'm going to just draw in the path that would take me to that point. So I've essentially come out a distance of X, over a distance of Y, and up a distance of Z. So I can label the sides of this parallelogram as X and Y. This would also be Y. And then this vertical distance here would be Z. Now the advantage of being in the first octant is that X, Y, and Z are all positive numbers, and so they're legitimate values for distances. What would change if I were in a different octant? If X were negative, for example, then I wouldn't label this side length as X, I would label it as absolute value of X, because lengths or distances cannot be negative. Okay. So I don't need to worry about absolute values in this case. Now, what I'm trying to calculate here is the distance from P to the origin. So I'm going to just draw in the straight line connecting those points. I'm going to label D is the distance that I'm trying to calculate. Okay. And I'm going to calculate that as the hypotenuse of a right triangle. What I'm going to do is I'm going to draw in another line right here. Okay. This would be in the XY plane. If P is the point XYZ, down here, this would be the point XY0. We actually call that, it has a name, we call that the projection of XYZ onto the XY plane. The projection is what we get if we just drop a perpendicular, in this case straight down, although if I had a point that was below the XY plane, I'd drop my perpendicular straight up until I hit the XY plane. So it would be the point that's directly, in this case, below P on the XY plane. Okay. So what that means is that this is a right angle right here, because this line is on the XY plane. This is perpendicular to the XY plane. So I've got this nifty right triangle that I'm going to draw. I'm trying to find this side D. This side is Z. I need to figure out what this side is right here. But this side is itself the hypotenuse of another right triangle. Doesn't look like a right triangle, but this is a right angle right here. Because here I was coming straight out and then going straight to the right. This is the x-axis, this is parallel to the y-axis. So I've got this triangle right here. I'm going to just label this side as A for now. Okay. And that's essentially the base of this triangle right here, whose hypotenuse is D, the distance that I want to calculate. Okay. So I'm going to just draw this right triangle here. Now I'm just redrawing it with a slightly different orientation, X, Y, and A. If I were in the XY plane, X would be a horizontal distance, Y would be a vertical distance. So I'm just drawing that with the standard orientation we would see in the XY plane. Here it's got a different orientation because it's on the XY plane in 3 space. Okay. But now I can easily just use the Pythagorean theorem here to get that A is the square root of x squared plus y squared. And then I use the Pythagorean theorem again. Okay. So I know that a squared plus z squared will equal d squared. A squared would be x squared plus y squared plus z squared equals d squared. Now algebraically that would have 2 solutions, plus or minus the square root of this. But since d is a distance and distances are not negative, the distance is just the square root of x squared plus y squared plus z squared. And it really does come from using the Pythagorean theorem. I'm just using it twice, once to get the length of this leg and once to get the hypotenuse, which is the distance that I wanted. Okay. Now, as I said, we worked with a point just for convenience that was in the first octant. All that that meant was that I could label these sides as x, y, and z. I didn't need absolute values. If I were in a different octant, I'd put absolute values around them. But if you look at the work that we do, we're going to square them, and so the absolute value becomes irrelevant. So it will always be the case that the distance from a point to the origin is just the square root of x squared plus y squared plus z squared. Okay. So let's just say we've got a point P. Let's let P be 2, negative 3, 4. And let's let Q be 4, negative 1, negative 2. I want to do two things. I want to find the distance from P to the origin. And I want to find the distance between P and Q. Okay. So I've given you the formula for this, so all you're doing here is plugging into the formula. I haven't given you a formula for the distance between 2 points. What I want you to do is pause the video, see if you can figure it out, or at least make an educated guess, then turn the video back on and we'll compare answers. Welcome back. Okay, for the distance from P to the origin, that's just going to be the square root of 2 squared plus negative 3 squared plus 4 squared. So that's the square root of 29. Okay. Pretty straightforward. For the distance between P and Q, okay, basically what's happening is instead of measuring the distance coming forward and back from a point to the origin, I'm looking at the distance forward and back between P and Q. Well, that's going to be a distance of 2. That's the difference between 4 and 2. And instead of looking at the left and right distance between a point and the origin, I'm comparing the left and right distance of these 2 points. That's going to also be 2. That's the distance between negative 3 and negative 1. Okay. And then when I look vertically, again, instead of comparing the vertical distance of one point to the origin, I'm just comparing to a point that's now 2 units below the origin. So the vertical distance between these points is going to be 6. Okay. So the distance between P and Q is the square root of 4 minus 2 squared plus negative 1 minus negative 3 squared plus 4 minus negative 2 squared. Now you might notice I didn't subtract in a consistent order. Here I started with 4 and subtracted 2. Then I started with negative 1 and subtracted negative 3. So I was always starting with the value at Q and then going to P. But here, for the Z component, I started with the Z value at P and subtracted the Z value at Q. So I was not consistent in which point I started in. I was consistent in making it so that I always got a positive number. This is going to be 2 squared plus 2 squared plus 6 squared. It actually doesn't matter. Because we are squaring these things, it does not matter what order you subtract in. However, do be careful. There are times when the order in which we subtract will be important. If we're not ultimately going to square that difference, we know that the order in which we subtract things affects the sign of our result. Okay. Here, let's see. This would be 4 plus 4 plus 16. This would be the square root of 24. And if I want to, I can simplify that to be 2 root 6. Okay. In general, on timed exams in this class, I'm not going to be super picky about you simplifying radicals. The reason is, right now, the problems that we're doing are pretty quick. This didn't take a ton of time. Okay. As we move through the semester, some of the problems start to be fairly time-consuming. And so on a timed exam, I don't want you spending a lot of time trying to get things into simplest form. I wanted you to just show that you've learned the material for this class. However, when things aren't timed, it's a good idea to practice getting things in simplest form, and as you're doing the homework and checking your answers in the back of the book, you'll generally be doing that. Okay. All right, so I just did an example of a distance between 2 points. Let me give you the general formula. Okay. So if P is a point x, y, z, and Q is a point x naught, y naught, z naught. So putting subscripts on the x, y, and z. The distance between P and Q is the square root of x minus x naught squared plus y minus y naught squared plus z minus z naught squared. And of course, you can do this subtraction in whatever order you want because you're going to end up squaring the result, which will make it positive. Okay, excellent. Now, there are a couple of other distance problems that we can take a look at this point. Let's suppose I have a point P. Let's make it -2, -3, 5. Okay. And let's say I want to find the distance to the xy plane, the xz plane, the yz plane, so the 3 coordinate planes. And while we're at it, let's find the distance to the x-axis, to the y-axis, and to the z-axis. Now, I haven't told you how to do that yet, but what I'd like you to do is before you watch the next video, just see if you can figure this out, at least make an educated guess, or if you don't get it, at least spend a little bit of time thinking about it before you turn on the next video, and then we'll talk about how to find these distances. We will eventually this semester be able to find the distance from a point to an arbitrary plane or an arbitrary line. These are very special planes and very special lines. And so there's a nice shortcut that we can actually figure out now without knowing a whole lot. We're going to have to learn how to describe general lines and general planes in 3-space before we can find the distance to other planes. But the coordinate planes and the coordinate axes should be able to figure out at this point. So give that a shot and then tune into the next video.